Hopefully you're here for Variational Inference in Python. My name's Austin. I'm a data scientist in Monotate Labs. I'll talk a little bit about Monotate at the end because they paid me to send them here, so I got to plug them a little bit, but that'll come at the end. I like to say I'm a recovering mathematician, so I'm really excited to be able to talk to you all here about math and Python and how they can come together, and Python can enable you to actually do less math by hand than you might have had to do, a year or 2 years ago to achieve the same results. And I'd also like to thank you all for coming, and the Capital One and the PyData DC organizers for this conference, because I'm a minor organizer of Data Philly. I'm from Philadelphia. We're kind of in preliminary talks with the Continuum Focus folks around having a Data Philly conference, and boy, is it a lot of prep. So for an event to be this excellent, they've done a lot of work, and so I really appreciate all the work they've put in. So let's just start by kind of going over some details of Bayesian inference, because variational inference is really kind of just another approach to Bayesian inference. This is one of my favorite pictures. I think it's from a statistics department somewhere in the UK. I really want one. I'd love to expense it sometime, but I don't think my boss would pay for it. Right, and so what does this actually mean? Well, the posterior distribution in Bayesian inference is the joint distribution divided by the marginal distribution of the evidence. Hopefully, we're all at least vaguely familiar with this. Not too many formulas in my talk, I promise. We're going to get to the Python pretty quickly. The problem is, for many useful Bayesian models, the marginal distribution of the evidence, this green quantity, is hard or impossible to calculate analytically, right? And so we have to resort to some kind of approximate computation. And there's a bunch of kind of standard, what I'll call modes of Bayesian inference, right? Or you can just restrict yourself to conjugate models where you can do that calculation. That's no fun and kind of limits what you can do. Markov chain Monte Carlo algorithms, I think, are probably the best known and most widely used. There's a bunch of other ones. There's approximate Bayesian computation, which I'll admit to not knowing a lot about. And then there are what are called distributional approximations. So there's Laplace approximation, which is kind of like the fundamental trick of statistics applied to Bayesian inference. And what's the fundamental trick of statistics? Write a power series and throw away everything that's higher than the linear term or higher than the quadratic term. It's like the fundamental trick of introductory statistics, right? Applied to posterior computation. And then there's INLA, iterated nested Laplace approximations, which I also won't say a lot about. But there's also variational inference. And one of the really exciting things is that over the past couple of months to year or two, there have been some nice emerging tools to automate variational inference in Python, piggybacking off of some theoretical advances in terms of performing variational inference not by hand on a wide range of models. So that's what I'm here today to talk about. So first, let's kind of get a picture of what normally happens, right? What's the Markov chain Monte Carlo algorithm, which is probably the most used approximation, right? What's the fundamental idea? Construct a Markov chain whose stationary distribution is the posterior. The amazing thing about MCMC algorithms is that this is possible a lot of the time, but we take this for granted now. Sample from the Markov chain for what I'll call a long time. What a long time means is actually one of the things that I want to talk about here, and then approximate posterior quantities based on the empirical distribution of those samples, right? And so here I just have a little animation of a Hamiltonian Monte Carlo algorithm exploring a normal posterior distribution. Okay. And so now let's get down to the Python, right? This is a PyData conference. We want to start interleaving Python and math pretty quickly. So throughout this talk, we're gonna lean on kind of the simplest Bayesian model you can have, the beta binomial model, right, to illustrate some concepts. Then we're going to ratchet up to more interesting models to give you just a teaser of what you can do with these Python packages. So suppose we have 3 successes in 10 trials, right, and we want to infer the true success probability. Well, let's put a uniform prior on the true success probability. And one of the 2 Python packages we're going to be talking about is PyMC3, which you'll see me using here. Right, and so this is how you translate that math into Python using PyMC3. You declare a PyMC3 model, and you say, okay, the probability of success in my beta binomial model is uniform between 0 and 1. I am somewhat of a contributor to PyMC3, minor contributor, I would say. I really enjoy it. And I find it really fantastic that you can kind of just translate from that math to that Python somewhat intuitively. All right? And then the probability that we have a success given our odds of success, well, that's just P, right? And then so we translate that into this Python, a Bernoulli distribution with P beta binomial as its probability of success. And then what's really neat is there's this observed keyword here that fixes, that says, hey, we've observed the number of successes. We've observed 3 successes and 7 failures here. So this is how you kind of fully specify this model in PyMC3. Right? And the advantage of this is this model is conjugate, right? We know the true posterior distribution is beta 48. I hope I haven't made the embarrassing mistake of forgetting to add 1s to each of those, but I think I did it right. So we know the prior and we know the true posterior. So this is going to be kind of our basis for thinking about variational inference a little bit. Now what does Markov chain Monte Carlo do to approximate this? Well, we take our model and we do this pm.sample, right? I said we sample from some Markov chain for a long time. Right, in this case, 50,000 iterations. And hey, we can approximate our true posterior distribution pretty well by the just empirical histogram of those samples, right? That's pretty good. So this is kind of the basic idea of Markov chain Monte Carlo. There's a million different flavors, but you get the idea now. So what are the pros here? Under some fairly mild conditions, this is asymptotically unbiased, which means it'll get you the right answer if you wait long enough. For some definition, like I said before, of long enough. Algorithms are somewhat model agnostic. You can give some model agnostic algorithms. You can, of course, speed things up with model-specific algorithms, but that's fine. And well studied for probably a while, right? Since at least the days of the Manhattan Project when they had this idea of approximating hard integrals through simulation. What are some of the cons here? It can take a long time to converge, right? Like I said, a long time. And sometimes it can be difficult to assess convergence because you don't know what you're supposed to be converging to, right? And also it can be difficult to scale. It can be difficult to parallelize, like, you can't just throw this thing out on a Spark cluster and expect it to give you the right results. You need to synchronize too often. There's a lot of overhead here. And I have a list of references in the back. There's one really great mini book that went up on the archive recently that discusses kind of exactly what the difficulties are there that I think everyone who's interested in this at a technical level should read. So now that we kind of understand what the kind of default go-to for Bayesian inference in analytically intractable models is, let's introduce something else, something that tends to be a little more exotic, variational inference. So what's the basic idea of variational inference? Instead of trying to find the true posterior eventually, what we do is we choose a class of approximating distributions, and then we find the distribution in that class that's closest to the true posterior, okay? So this is interesting and introduces some interesting trade-offs that we'll talk about in a second. Just on a kind of technical level, it minimizes this Kullback-Leibler divergence from the approximate distributions Q to the true posterior that we can't actually compute in red. And this is interesting. This kind of gives us a little grounding in information theory, right? Because what is minimizing this actually minimizing? It's minimizing the number of bits, extra bits you need to encode samples generated from your variational distribution using a code optimized for your true posterior distribution. It's not super important. It's a distance measure between distributions, but it's an interesting connection with information theory. Right? The thing is, we can't calculate that red quantity up here. So this formula is basically useless to us. How do I calculate this without calculating the red quantity? Fortunately, through the power of logarithms, that expands to this, right? Where we have this bracketed distribution, this bracketed quantity that I'm calling the elbow, evidence lower bound, plus that green distribution, the marginal distribution of the evidence, which is hard to calculate, but doesn't involve Q, so we don't care, right? If we're trying to maximize or minimize this in terms of Q, we can ignore that green distribution, because that's just a number that doesn't depend on the variational distribution. Cool, and I mean, if we can't calculate the joint distribution, we have other problems and should resort to other methods. So enough variational inference theory, let's dive into a quick example, quick visual example. Suppose this is our true distribution that we're trying to approximate using variational inference. Now, this we could probably calculate by hand, but whatever, it's instructive. And the variational family we want to choose is not, right, this is a two-dimensional Gaussian, but it definitely has a full rank covariance matrix, right? Things are definitely correlated here. Suppose we want to approximate this with uncorrelated Gaussians, right? Gaussians that are with diagonal covariance. Okay, we can do this, and there's, oh, I actually meant to do this at the beginning and then got excited. I tweeted the links to the slides and the notebook my talk is based out of, because if you've ever looked at something like this is actually generated from an IPython notebook. And it's just at Austin Rochford, my first name, last name. I'll post that again at the end of the talk. So as you can see, here's the notebook this talk was generated from, and here's a Docker file that contains all the dependencies, because some of them can be a little difficult to install. So hopefully this talk should be fully, reproducible on your computers if you're interested in it afterwards. So here's the variational approximation we get if we ask our normals to be uncorrelated. Now we can see it's smaller, we tend to overstate our confidence. So what are the pros and cons of this? Well, the pros in my mind, and this is what really matters to me in my professional life, because I use these methods professionally, is that it's a principled way to trade complexity for bias. Right? The true posterior distribution required 4 covariance parameters. The approximated covariance distribution required 2. We've reduced the complexity from n squared to n. Right? If you're a software as a startup company that mine is, you have a couple hundred clients, each of which has a couple thousand models. You need to store these in a database. You need to pay Amazon for the disks to store them on. That reduction saves your company money. Lets you predict faster. So one of the things I really like about variational methods is that they give us a principled way to say, hey, I know I'm not going to get the right answer, but I'm going to get the best answer I can under the complexity constraints my application can tolerate. And another great thing about it is that optimization theory is applicable, right? People have been working for a long time on optimization algorithms. So instead, we changed the posterior calculation from sampling to optimization, and right, a little easier to assess convergence sometimes here. There's all kinds of scalable optimization methods that have really enabled machine learning over the past 20 or 30 years, right? So people are really good at parallelizing optimization. So this is exciting. It's not all roses, right? There are trade-offs in everything in life. What are the cons? Well, it's a biased estimator of the true posterior. We just kind of buy that when we buy this. We say, we have to see if we can live with that bias in every situation. So sometimes it's better for predictive accuracy than interpretation. I wouldn't necessarily want someone making policy decisions based on this, right? If 2 variables are correlated, that's important to know in a policy decision, and if we force them to not be correlated in our answer, that might not be the greatest. And a lot of the time there are model-specific algorithms you have to derive by hand. And I don't really want to go too deep into this slide if this matters to you. Mean field variational inference assumes all of the quantities are independent in your approximating class. And you can use coordinate ascent from this. And actually working out this first equation, that's where a lot of the hand calculations come in. It's easy for things in exponential families. It's a little difficult other times. It's tedious and can be slow to converge because you're updating one parameter at a time. So let's talk about how we can automate that, how we can not do calculus by hand with Python. I taught calculus for 5 years while I was in grad school. By all accounts, I'm pretty good at it. I still don't like doing it by hand. Right? So if I can get Python to do calculus for me, I will. So the main theme of automating variational inference in Python is kind of 2 things. One, we want to maximize the elbow using gradient ascent instead of coordinate ascent. That'll go faster. And 2, we want to use some tensor libraries, I'll clarify what I mean by that in a second, to calculate the gradients automatically, to do calculus for us. So here's kind of a table of the 2 Python packages I want to talk about, the tensor libraries they use, and the variational inference algorithms they implement. The first is Edward. It's out of a research group in, I believe, NYU or Columbia. I think Columbia. It uses Google's TensorFlow to do calculus under the covers and parallel computing, all sorts of stuff like that. And it implements, among other things, I'm simplifying here, but what we're going to talk about today is it implements black box variational inference. And then there's also PyMC3, which, like I said, I'm a little more experienced with. I use a lot. Its tensor library is Theano, if you've ever heard of that. It's kind of a neural network. It started in the neural network world, but it's useful for a lot of other things. And then it implements something called automatic differentiation variational inference. And we'll talk about what that means in a second. So what are some of the common themes here before we dive into actual calculations? We use Monte Carlo estimates of the gradient. Okay, so this is a bit like stochastic gradient descent, right? And we use mini batch estimates of the joint distribution to make this scale. So a lot of data. And like I said, this is a notebook, and the great thing about slides in notebooks is you can have hidden cells. That's how I'm producing all these figures without showing you a ton of matplotlib code. Well, I also included a lot of math there for those that are interested. So dive into those hidden cells if you're interested in the math behind this that I'm leaving out right now. So black box variational inference and ADVI, they just arise from two different ways of calculating that elbow gradient. You can do that calculus a couple different ways. You get some different methods. So now let's dive straight into Python, some Python examples. Black box variational inference is model agnostic in some sense. And like I said, the math details are in here. It requires the ability to evaluate the joint distribution. Okay, well, if you can't do that, we've got bigger problems. And you only need to differentiate the variational distributions to calculate elbow gradients here. This is Edward's icon, logo, whatever. It's a black box. It's pretty clever, I thought, so I just put that in there. So let's get back to our friend the beta binomial model and see what does Edward do with the beta binomial model. So here's how we express that same model we did before in PyMC3 in Edward. Right? We say P is uniform between 0 and 1. X is a Bernoulli variable with probability of success P. This is all pretty much the same, slight differences. One had a context manager, one didn't. Then we map the data to the same NumPy array. We say, hey, this is how we tell Edward this X Edward beta binomial was observed to be those 3 1s and 7 zeros. Then we tell Edward what variational approximation we're trying to use. We say, hey, we're going to say the posterior is also a beta distribution. Well, because it is, right? And this TF positive variable, that just is some bookkeeping. I've buried that in a hidden cell to get TensorFlow to generate a variable it can optimize, but constrain it to be positive. You can look at the definition, it's not that hard. And then we say, hey, in your approximation, replace P with QP. That's pretty reasonable, nothing too difficult here, right? And then we say go, do mean field variational inference with this system and this data. Run it for 10,000 iterations. And hey, we get something that looks vaguely like the true posterior. Reasons we don't get the true posterior, the distance is non-convex, so we can converge to local maxima, et cetera, et cetera. But this isn't too bad, right? This isn't the worst thing in the world. Peaked in the vaguely right region. Well, like I said, Edward implements black box variational inference. And one of the really cool things about this is it doesn't care how you tell it the probability model. So here we use this Edward.model stuff for P and X, right? That's a thin wrapper around some TensorFlow distributions just so Edward can do some bookkeeping. So that's really TensorFlow going on for P and X. Well, since it doesn't matter, Edward can actually take a PyMC3 model and perform inference on it. Because remember, the only thing Edward needs to differentiate is the variational distribution. So we can specify the probability model in PyMC3 here. And one important thing is that transform be none. We'll talk about what that means eventually. Pretty similar. And then we say, okay, here's the variational posterior. Here's the system. Go do it. Right? We're still specifying the posterior using TensorFlow because Edward needs to differentiate that. And hey, we get something close. If you ran them for a long number of iterations, they should converge to the same thing. There are tests to that effect in Edward's test suite. So this is interesting. It's actually quite model agnostic. And you can see that because Edward supports a lot of modeling languages. The first we saw was those TensorFlow distributions. That thin wrapper around TensorFlow, that was Edward.models. Second is PyMC3. It also supports Stan, if you're into that. I'm not a big Stan user, but it's just a Markov chain Monte Carlo library in C++. Wrappers in R and Python. It's kind of big used by Andrew Gelman and people like that. You can also do direct density calculations, and I'll give an example of that. You can do that in TensorFlow, and it'll parallelize it a little bit for you. You can do it in NumPy, or you can do it in pure Python. Quite flexible in what it accepts. So for each of these Edward and PyMC3, how I'm going to kind of structure this is, I want to give you a simple example of the beta binomial model to wrap your minds around what's happening. And then I just want to tease how you can get more complex and fit some interesting models in these things as they are now, even though they're kind of rapidly evolving. So since we're in Washington and it's almost election time, I wanted to do one of my favorite examples as an armchair political scientist, congressional ideal points. So I've taken the University of California, Irvine's data set on 1984 congressional votes. I've loaded it here and I've coded it with 0 as voting for the bill, or voting against the bill, 1 is voting for the bill, nan is not voting, and coded party, I think it's 0 as Republican, 1 is Democrat. You can see this all in hidden cells. Like I said, I have this all spelled out. We want to see how can we use just this vote data to separate Democrats from Republicans using Edward. So here, this just kind of shows you what percentage of each party voted for each bill. That's kind of interesting. Just kind of some EDA on this data. What's the idea of this model? I want to give the idea and then how that translates into Edward, and it's pretty intuitive, I think. Representatives and bills each have an ideal point on a spectrum of conservatism. Political scientists have chosen to call it conservatism instead of liberality. I don't know why, but yeah, you just kind of fix which direction is up, right? It's like physics. It doesn't matter which direction is up as long as you're consistent. So if a representative and the bill have the same ideal point in terms of conservativity, there's a 50% chance that representative is going to vote for that bill. Right? Bills also have an ability to discriminate between representatives, right? Because some bills have broad bipartisan support. They're not very good from telling ideology, and some are voted along party lines. Right? This is really all we need to know to put this model together. So we put some priors on here. I'm going to show the prior and the code necessary to implement it using Edward. Right? So the representative ideal points we just assume have standard normal distributions, right? This isn't too bad. We take a normal distribution, ask for its log PDF, add it up using TensorFlow. Bills have ideal points and discriminative abilities. These are hierarchical normal distributions, right? Normals that are constrained to have same means drawn from the same distribution, variance drawn from the same distribution. Why doesn't alpha have a hierarchical system? Technical model identification reasons. There's a paper I put in the references you can read that's what you need to do to identify this model. Right? And this is how we implement that, right? We just have a log normal prior on mu, a uniform prior on sigma, and then we evaluate the prior just as before. So then this is just a logistic regression model kind of given those things, right? Alpha minus beta times gamma, stick it through a sigmoid, right? So here, we basically have that. I love seeing how math translates almost exactly to Python, right? Sigmoid of gamma times the quantity alpha minus beta. And then just the Bernoulli log PDF on that. It's really, really beautiful and concise. So to get those functions into an Edward model, it's really simple. You have to do some bookkeeping where you unpack the parameters from these dictionary x's and z's. You evaluate the prior, you evaluate the likelihood, you add them. We put together our variational distributions. You can read a little more about this later. I'm a little behind, so we're going to move forward. And we say, hey, do mean field variational inference on these. Run it for a while. Cool stuff. And hey, look, we look at the posterior distribution of endpoints, and we have separated Democrats from Republicans in very few lines of Python fairly quickly. So this is just neat, and like I said, not like comprehensive. If you wanted to use this model in real life, there are other things you would do, but just to tease the things you can do with these libraries is my goal here today. A fun project here, and like I said, I'm super interested in this sort of thing, would be to recreate this dynamic ideal point model of the US Supreme Court in Edward. I think we're like 70% of the way there with this code. Right? You just need to add a time series for some of these things. I think that would be a neat thing that I may do eventually, but would also be happy to read someone else having done. So, like I said, moving quickly because I'm a little behind, but it's the last session of the day. You don't mind if I keep you from happy hour a little long, do you? No, I promise I won't go too long. If we need to take questions to the happy hour, we can always do that. Nothing wrong with that. So now we've talked about Edward and black box variational inference. Let's talk about variational inference in PyMC3. So this uses something called automatic differentiation variational inference, which is a mouthful. Here's the idea. It's only applicable to probability models where you can differentiate everything. Okay, so here we are explicitly requiring the model be differentiable, where we weren't in BBVI. What you do is take parameters that have constraints on them, like a parameter that lives in 0, 1, transform it to live on the whole real line. Log odds transform. I'll show this in a second. Approximate all unconstrained posteriors with the closest normal distribution you can, and then transform back for things you have to. So let's see how the beta binomial model works with this. So again, in the constrained parameter space where the probability of success has to lie between 0 and 1, we've seen this picture on the left before. What we do is we take this log odds transform to allow that parameter to live on the whole real line. The equivalent prior and posterior are on the right. Okay. So now what did I say ADVI does? It'll approximate that blue distribution on the right with the normal distribution that's closest to it. So I do ADVI on it. This is the same model I used at the very beginning, by the way, right? These things are reusable, they're pluggable, which is, a really nice kind of software engineering feature. You can either sample from them or do variational inference on them. And so this red curve is the ADVI approximation to the transformed posterior, right? And then I said we pull that back to the constrained parameter space. Hey, and we get a pretty good approximation. We get what's probably a better approximation than the Edward one. Well, that makes sense because we're putting more assumptions on the model in this case, right? So we can get more out of it. That makes perfect sense, right? When you put more assumptions on things, you can usually get more out of them. So the example I'm really excited to talk about here, and this is just one of my favorite models because I really love Bayesian non-parametrics because I really hate model selection. I really, really hate fitting a ton of models, cross-validating, whatever. Any chance I get to push model selection into model fitting, I will take. So I really love Bayesian non-parametrics because we're going to model this as a mixture distribution where the model selects the right number of mixture components in a hypothetically infinite number. We're going to do this on a computer with PyMC3. It's going to be awesome. So here's some data from Larry Wasserman's excellent all of non-parametric statistics. He uses in a lot of examples we're going to use here. It's interesting data. It's got a couple of different trends in here. It's not homoscedastic, right? The errors, the noise varies with X. I always have to make sure I get the term right. So what's the idea that we're going to implement here? A mixture of linear models with an unknown number of mixture weights and the mixture weight is allowed to depend on the X variable all at once. To kind of illustrate the things you can do with PyMC3. So just an idea, hey, here are 3 lines that look like we might be able to mix them to fit this pretty well, but I don't know. Let's let the data decide, right? Like I said, I hate model selection. Push it into model fitting whenever I get the chance. So let's put a prior on our mixture weights, right? So we're going to do what I call a logistic stick breaking process. You can read a paper about this in my references, right? And we basically just have regression coefficients, alpha and beta. So alpha plus beta x. We're going to put that through a sigmoid function. Then we're going to do something called the stick breaking process. Not that important. You can read about it in some of the references. This is how we turn this prior into a prior on infinitely many weights. Okay. And I say infinitely many, but we actually truncate to k here. We'll see why that's all right in the end. Because, right, computers can't compute with infinitely many things. They're bad at that. This is how this model gets translated into Python. It's pretty intuitive, I think. I really dig this. There's some magic hidden in the stick breaking function, but I promise it's not that much magic. And you can read what it is in one of the hidden cells. One of the really neat things here to pay attention to is I've declared this x lidar as a Theano shared variable. We'll come back to that in the end. That lets us do easy posterior predictions with that x. We'll see what that does in a minute after we finish specifying our linear model. Then, right, we said a mixture of linear models. So here's just, a k Bayesian linear models for each component, right? I'm not going to dive too much into this, but this is not direct translation from Python to math. Again, a thing that makes me really happy. And then the observation model is just a mixture model, like I said, right? It's the ith linear regression with probability xi. And this is how we specify that. So we take this, we say with our LiDAR model, let's do some ADVI, right? We get this beautiful elbow chart, right? This beautiful graph of the evidence lower bound, which looks like it's converging, right? One of the benefits I said of this is a lot easier just to visually diagnose whether you're converging or not. And notice, since we're getting noisy estimates of the elbow, right? If you're used to like EM algorithms or convex optimization, this is not increasing at every step, right? You might in a lot of optimization routines, you might look and say, crap, my code has a bug, because this should be increasing every step. Since we're using noisy estimates here, that's not the case, but that's okay, we're increasing in general. And one of the really cool things about PyMC3 that you can also do, that I said before, was using that shared variable. That basically tells Theano, hey, I may change the value of this later, pay attention. So here, I set just a grid of points that I want to predict at. STD range is the standardized x value here, or just 100 grid points between the smallest and largest. I swap the x variables I fit the model with for the x variables I want to predict on. And then I ask PyMC3 to do posterior predictive sampling for me. It's pretty cool. This takes a little while. And we can examine first the impact of that truncation I said. Now, if we truncated too soon, we would see mixture weights with positive mass on them all the way out to the right here, or pretty far to the right. Right? So the fact that there's no mixture weight with appreciable positive mass in it past 10, we probably did an okay job truncating. And this is a heuristic, it works pretty well. There's a paper in the references you can read about truncated stick breaking processes. And hey, here's our posterior prediction. And it looks a little wacky, right? It's a little jumpy because of our bias, but that's pretty cool. Right? I think it's pretty neat that we did this Bayesian nonparametric mixture with potentially infinite number of components, where the component weights depended on x, all on my MacBook without too much work, without blowing it up too bad. So this is kind of what you can do in PyMC3. There are some references here that you can get in the linked section on Edward and PyMC3, variational inference in general, models, some of the specific models. So whatever you're intrigued on learning more here, I hope I've sparked your interest to learn a little more about something here. And that book I mentioned is this Patterns of Scalable Bayesian Inference. At least skim it if you enjoy this sort of thing. It's really interesting. Thank you very much. My name's Austin. I'm a data scientist in Monotate. We're an e-commerce software as a service company. We have 8 years of e-commerce interaction data to play with, 100 billion page views we observed in 2015. We witnessed 1/3 of US e-commerce dollars spent. It's a really fun place to work, a fun place to do modeling. We're not hiring at this exact moment. We will be again in the future, and I love to be in touch with smart people when we are. So please come get my business card, give me yours. Ask me questions about Monotate maybe at happy hour or variational inference now. And just thank you so much for your attention and to the PyData DC people for putting this on. Oh. Does anyone have questions? Yeah.
Can you click on that here link so I can see the URL?
Certainly. It's uninterpretable. But like I said, I did tweet it from just at Austin Rochford. So if you look on the If you look at me, it's really just at my name on the conference thing. There's a tweet that'll take you to the link to the slides and the notebook. Does that answer your question? Sorry, it's a bit roundabout.
Page. I didn't see it there. So.
Yeah, it's a gist. Sorry. Yes.
How did Wasserman solve that problem?
You know, I have not read that book in a while. My guess would be something like generalized additive models, smoothing splines, something, but I haven't read that book in a while. That's just an example I have in the back of my mind.
Which problem is that?
The LiDAR, where it's a mixture of linear things that's not homoscedastic. Like I said, I always screw that up. It's a lot of letters to get out. Any other questions? Yeah?
So in the work that you do you actually use the posterior distribution, or do you take point estimates and use that for?
Right. So I should be better about repeating the question for those who will watch the recording later. The question was, in the work I do I use the full posterior distribution or do I just reduce it to point estimates? The answer is yes, I use the full posterior distribution a fair amount. It's really useful in like some active learning algorithms that require randomization to have beliefs that already have a distribution to them you can just sample from for your next belief. So situations like that, I definitely do use the entire posterior distribution and do not reduce it to a single point, and it's actually kind of crucial for those situations. And like I said, Edward and PyMC3 kind of emerging. I'm putting them into production. I use them sometimes for EDA. I've certainly used to great effect kind of hand-calculated variational inference at work to do exactly what I said before. Turn difficult problems from sampling problems to optimization problems, turn them into streaming inference, and reduce the memory complexity. Like that's a thing I've been able to do a lot at work, and so it's I think a really profitable thing to learn if that's your niche. Really useful thing, not just as a mathematician I find it intellectually stimulating, but it's also done a good job for my company. Any other questions? Yes?
So you mentioned that this gives you a principled way to tackle the bias variance trade-off. With regularization approaches, you kind of have like a parameter to slide around. It appears to me that the way you get at the bias variance is to choose your class of models. Is there any analog that's like, a tuning parameter for the bias variance trade-off?
Well, and so this isn't exactly the bias variance trade-off, right? Because we're trading like complexity for bias here, right? And actually, a lot of times we will end up increasing bias and underestimating variance. The lever you can really pull there, and there's not like as much of a cross-validation way to pull it as there would be with like lasso or ridge regression, which are Bayesian inspired, if not exactly Bayesian. Is that variation, that class of approximating distributions, right? If you make those more complex, it's going to be a harder optimization problem, but you're going to get less bias. If you make it less complex, it's going to be an easier approximation problem with more bias. So that's kind of the lever you can pull here. And that's what's really interesting. You can say, hey, I can only tolerate linear covariance parameters. Do the best you can. So that's the lever you can pull. Does that make sense? Any other questions? Awesome. Well, thank you all so much for coming and listening to me talk about math at the end of a long 2 days. And like I said, feel free to find me out in the hall if you have any other questions about this or Monotape you'd like to ask.